Welcome to EDU World Space.
So if we want to find a tangent line at this intersection between these two curves at this point over here, the first thing we need to do is actually come up with some kind of parametric equation. So what I'm going to do, since these are cylinders, I'm going to come over here and first use the fact that if we said x is equal to 5 cosine theta, and then y is equal to 5 sine theta, this would parameterize this over here. And I guess you could use t if you want, but I normally just use this. So we have that. Now we need to solve for z. So what we can do is take this, come over here, plug it in for y, and then just solve for z. So that is going to give us 25 sine squared theta, and then plus z squared is equal to 20. So we subtract square root. So we get z is equal to first plus or minus the square root of 20 minus 25 sine squared theta. And we're going to only use the positive root for this since z is supposed to be 2. If this was negative, then we would want to take the negative root. But in this case, we're just going to keep it as the positive root. Okay. So this is what we have so far. So we have some parametric equation for these intersections. So the intersection we can define as r of theta being 5 cosine theta, 5 sine theta, and then the square root of 20 minus 25 sine squared theta. So this is going to be our parametric equation. Now what we need to do is figure out what is theta going to be at, and then we can take the derivative and kind of go from there. So I'm just going to go ahead and use the fact that we know x is supposed to be equal to 3 at this point. So we're going to have 3 is equal to 5 cosine theta. So we can go ahead and take arc, or divide by 5, and then take cosine inverse on each side. So we're going to get theta is equal to cosine inverse of 3/5. Right. And I guess just kind of for simplicity, since we'll need to plug this into sine as well, I'll go ahead and plug that into there also, just so we don't have to work as hard later and think, okay, what is sine of cosine inverse? So this is going to be 4 for the y is equal to 5 sine of theta, so move things around, and we'd get theta is equal to sine inverse of 4/5. So we'll use both of those later on. But in the meantime, we need to go ahead and find our derivative of this. So it'd be r prime of theta is going to be equal to, so the derivative of this is just 5 sine theta. The derivative of 5 sine theta is 5 cosine theta. And then to take the derivative of this, we're going to have to work a little bit harder. So we'll have to use power rule, so it'd be 1/2 20 minus 25 sine squared theta. Now this would be to the negative 1/2 power. Then we have to take the derivative on the inside. So the derivative of 20 is just going to be 0. And then it would be minus 25. And then we'd use chain rule. So it'd be 2 sine of theta. Then we take the derivative of sine, which is going to be cosine, and we multiply it. So this is going to be our derivative here. So now we can go ahead and plug in theta being cosine inverse of 3/5 or sine inverse of 4/5. So if we do that, this is going to give, so r prime of, and actually I'll just leave it as theta. So sine of theta is just going to be 4/5, so this would be 5 times 4/5. Cosine is supposed to be 3/5, so it'll be 5 times 3/5. And then this, well, first we could just go ahead and reciprocate that and then turn it into a square root. So it is going to be, oh, actually notice this 1/2 and this 2 cancel out. Okay. So this is going to be -25. So sine of theta, again, is just going to be 4/5. Cosine of theta is going to be 3/5. And then this will be all over the square root of 20 minus 25, and then sine again is 4/5, but we're going to square that, so 4/5 squared. Okay, now this 25 and those 5s cancel out, and then also this 5 and that 5 cancels out. Okay, so let's go ahead and simplify. Open to see that 5 and that 5 go away as well. So this is going to be 4, 3, and then that would be -12 over, so that would be 20 minus 4 squared, which would be root 4, and root 4 is just 2. All right, so again, we'd get 4, 3, -6. All right, so that took a while for us to get to, but we finally know what our vector is going to be just coming off of this. And now, if we want to find a line, all we really need to do is pretty much the following. So we're going to say this is equal to, so I'll just call this, or actually maybe I shouldn't call it that. I'll call it little t of theta. And this is going to be our derivative, so r prime of theta. Actually, that's probably a bad thing to use. So it'll just be r prime times t plus whatever our initial point was. So initial. Actually, I'll just write this out in words because the symbols I think are kind of throwing it off because I'm reusing stuff. But yeah, so it's just going to be the slope, so the tangent slope times t plus our initial point. And we can do this whenever we don't really care about like indexing t in some way. So let's come back up here. So our initial point is 3, 4, 2. And then we have our vector there, so that we could just go ahead and multiply this by t. So if we multiply that by t, that would give us 4t, 3t minus 6t. And then we're going to add our initial point of 3, 4, 2. And then we can just go ahead and add these component-wise. So we'd end up with 4t plus 3, 3t plus 4, and then 2 minus 6t. So this is just one possible parameterization. You might get something different, but I would say this is just like the most standard one to use.